So we left off having discovered that we can use matrix operations to figure out what's going on a vector field. And just to recall, those were the differential equations that we had simplified into a matrix. And if you remember, at the point 1, 0 on the YV plane, we found out that the vector field is pointing in this vector direction, 0, comma, -1, or if you want to think of it that way, right 0, down 1. So we could say this as right 0, down 1. And at 0, comma 1, we found out that it points in this direction, which is right 1, down 0, or up 0. Doesn't really matter, up or down 0. And at the point -2, comma 2, sorry, I made a little boo-boo there, we found out that it points in the direction, 2, comma 2, or right 2, not down, up 2. But what about some other point? What about the point 1, comma 2? Well, at the point 1, comma 2, we could plug that back into our matrix equation. But remember what the matrix equation is telling me. The matrix equation tells me the value of dy dt and the value of dv dt. And so we can just use these two as coordinates up here and say, well, this is the y value that we're plugging in, and that's the v value that we're plugging in. And so the dy dt is dependent only on the v coordinate. So this should point in the direction 2. This should be 2 because that's my dy dt. So it's just whatever the v value is. And the dv dt is the bottom one, and that's just negative whatever the y coordinate is. So this should be 2, -1. So this should be pointing right 2, down 1. And we can turn that into a pictorial representation of what's going on the YV plane. All we have to do is know that at a particular point, the vector field is going to point in a particular direction. So I'm going to translate each one of these points and each one of these vector field values onto the plane below. And so it's not all going to fit on the screen, so you have to have that stuff written down. So if you haven't written this stuff down, make sure you do that for starters. And so if I scooch this thing down, all we have to do is find on the plane the YV values. And so up here we start at 1, 0. And so 1, 0 corresponds to this point right here. 0, 1 corresponds to this point right there. -2, comma 2 corresponds to this point up here. And 1, comma 2 corresponds to this point right here. So we have 4 points on the phase plane that we're looking at, and we're asking really what direction will the solution curve move if we're right there, or we're right there, or we're right there. And each one of these is probably going to be on a different solution curve. But we can still ask the question, what direction should we go? And that is what gets answered by the vector field value. So for this first one, for this guy right here, boop, it's saying go right 0, down 1. And so I'm going to use some color coding here. And so I'm going to say that's this point. It's saying going right 0, down 1. And so right 0, down 1 means that I would have a vector field value pointing down 1 like that from that point. That's what it's telling us to do from this point right here. From this point right here, 0, comma 1, it's saying go right 1, down 0. So 0, 1, it's saying go right 1, down 0. So go this way to there. And so that point right there, the vector field is telling us to go that way. Now notice, remarkably different, these two are moving in different directions, right? So if you play the clock forward from this point, it's going to start moving this way. But you play the clock forward from this point, it's going to start moving down. That's what the vector field values are telling us. So if we take a look at this guy right here, -2, comma 2, that's saying go right 2, up 2. So negative 2 comma 2, it's saying go right 2, up 2. So it's going to go right 2, up 2, and the resultant is this vector right here. So it's saying don't just go horizontal, don't just go vertical, do both at the same time. And so that point, if we were on that point on a solution curve, it would be moving in that direction. And notice the length of those vectors is telling us something too. It's telling us how quickly we're going to move in that direction. And so last but not least, we have at 1 comma 2, it's saying go right 2, down 1. So here it says go right 2, down 1. And so the resultant vector is going to be something like that. So 4 different locations on the phase plane are telling us to go in 4 different directions as well. So each one of those points has a unique direction. So the purpose here, the point that I'm trying to make is every point on the YV plane, on that phase plane, has a vector, has an associated vector telling us which way to go. From there. So if you start at any point on the phase plane, the vector field value tells you which direction to go. But notice it tells us which way, and that's the direction. But it also tells us how fast, and that's the length of the vector. Length of the arrow, if you want to think of it that way. Or another way of saying it would be the magnitude and the direction of that vector. And so it's not just a slope field. It's not just telling us the direction. It's telling us how quickly to move in that direction. And so these two are moving relatively slowly compared to these two, right? Because the vectors are longer. Now, you might be thinking, oh, geez, so anytime we want to see a vector field, we have to plot points and do this? Well, in the old days, the answer would have been, yeah, you have to plot points and draw arrows and try to get a picture of what's going on. But of course, we're not in the old days anymore, and we have Maple. And so Maple can produce a vector field. Now notice, this looks an awful lot like a DE plot, but it's not a DE plot. So this is a vector field. And a vector field in Maple is a field plot. And in order to do this, we're going to need to have plots loaded. And so we need to have with plots, right, in Maple. And so I'm going to switch over to Maple. My Maple's being a little wonky today, but I'm going to switch over to Maple. I've got it pulled up already. And so what we have is a vector field. I just kind of drew one on a whiteboard here. If we had a vector field that looked like this, and we had to use that vector field to make some predictions, it would be a real pain in the butt if every time we wanted to look at a vector field we had to hand draw it. And so we have the ability to create field plot. So there's a couple things about the field plot command that are worth pointing out. First of all, you'll notice inside the field plot we're not actually listing things as equations. It's just the right hand side of the equation. So that, remember, our first equation was dy dt equals v, and in Maple land it always would have been, you know, dy of t dt equals v of t. But in field plot land, these are vector fields, and so we don't need to call it velocity as a function of time. We just write it as v, and the second one negative y. And then the next thing on my in the command is writing it as, you know, what are the window settings, basically. Horizontally is in the y direction, vertically is in the v direction. Now, if you change the order of those two things, it will completely mess up your vector field. So the order that you put them here, that's dy dt, and that's dv dt. That means y has got to be your first variable, and v has to be your second variable. Right? You have to do them in that order. And so you'll notice that if all I did was just that, then I could produce a really simple, straightforward vector field. And let me hit enter on this so you can see what happens. Nope, it doesn't like it because I forgot to, I reopened my document and I forgot to do everything got reloaded, but I didn't renew with my tools here. So let me scroll back down, and then hit it again. And you can see this is what a bare bones field plot looks like. And sure enough, the further you get out from the origin, the longer those arrows are. And if you remember, that's what we were seeing on our notes, right? The further we were from the origin out this way, the longer those arrows got. And we can see the same thing going on in Maple in our field plot. Now, there were a couple of other extras that I added onto this. And so the first extra was an option called field strength. And so what I like to do is tell Maple, I want my field to have a maximal field strength. The default is 1. I want it to have a maximal field strength of 2. And so that's basically going to make these arrows a little bit longer, but it's also going to make those arrows a little bit longer. I'm basically scaling up my arrow length. And so you'll notice by changing that maximal state, I've made it so that I can see the arrows that are closer to the origin, because those are pretty small arrows. The further out you are, the more pronounced the arrows are. And the other piece of information that I added to that was these arrows, you can change the size of the arrows. And so I'm just going to make arrows equals thin. And so it doesn't really alter this too much. But if you wanted to, you could change the arrows to, I think it's thick if I remember correctly. Yeah. Thick makes the arrows, well, a little bit ridiculous in this case. So arrows being thin probably is the way to go. Keeps jumping down whenever I do that. And so this appears to predict exactly what we thought would happen when, if you remember, we had the coordinates 1, 0. At 1, 0, it's going to be over here, 1, 0, and it's pointed directly down. That looks to be exactly what's going on. At -2, 2, the arrow appears to be pointed up and to the right, and that's exactly what we expect. So we can use this to make predictions about what's happening, what direction the vector field is going. But notice, each one of those arrows represents both a dy dt in the horizontal direction and a dv dt in the vertical direction. And so that's really nice for us because we're able to do some really useful things with this. But a couple of notes. The first one, you can't show particular solutions. You can't actually put a particular solution on a field plot. So the best you can get is just basically a fancy DE plot with variable length arrows. The other thing that's nice about it is you didn't have to type in the entire equation up here. But that's also the downside. You're not typing in the entire equation. You're only typing in the right-hand side in terms of the variables, not as functions. So those two notes I want to point out and make sure people catch. I'm going to switch back over to the document so we can kind of finish this page off here. So for a fixed length direction field, we can use this little option, field strength. Remember I did field strength maximal. This is field strength fixed, and really all that's going to do is produce our DE plot, right? This is our phase plane. This is the same as a DE plot or a phase plane. So you can quickly make a phase plane by typing in this information in here. You don't need to say the entire equation. If you want, you can just type this in. And so the very end of this page, the very bottom of this page, shows that our predator-prey model, we could do the same thing. We could plug this in and take a look at it. And that would allow us to make some predictions. And so for our predator-prey model, thinking way back to the beginning, if we wanted to look at any particular location on the phase plane, what it's going to tell us, the output for our, the output value for plugging in any R and F value on the plane, it's going to tell us what direction or at what direction, and how quickly I want to say A, I want to see the solution curve travels at any given point on the phase plane. So this is handy because it's basically allowing us the output of plugging in our values into this vector field allows us to kind of know what's happening. And if you remember, the vector field, we usually write it by, some kind of bold-faced V, and then I'm going to give it the coordinates 3, 1. So on my phase plane, you can think of this as being the R value up here, the rabbits, and that's F value, the foxes down there. And so if you remember correctly, our equation, and this is flipping back a couple of pages, was take your, in the top, it's going to be 2 times the R value, so 2 times 3, minus 1.2 times the rabbit value, times 3, times the fox value, which would be 1. And in the bottom of this would be the df dt equation. And that was always just negative the fox value, negative 1, plus 0.9 rabbits times foxes, 3 times 1. And so these are just numbers. And so what this spits out, if you do a little bit of number crunching, in the top you wind up with 2.4. And in the bottom you wind up with 1.7. And those two numbers are telling us something. This is saying the rate of change of the rabbit population at this particular moment is 2.4 per unit time, and the rate of change of the fox population is 1.7. Both of them are positive, so that means both populations are growing. And so in terms of the phase plane, we can think of this as saying at 3, 1 on the RF plane, so at that particular location, the solution curve points 2.4 units to the right and 1.7 units up. So right 2.4 and up 1.7. And so what does that mean? Well, you can do a little bit of analysis. You can do a little bit of geometry and say if we're going right 2.4 and up 1.7, a little bit shorter, we can figure out what is the resultant vector. And so this guy right here, at some angle, that resultant vector right there is going to be the square root of 1.7 squared plus 2.4 squared, which if you plug it in turns out to be about 2.94. And that number doesn't mean anything in terms of rabbits and foxes directly, but that is telling me how quickly the solution curve is changing. Right? That's the magnitude of the vector field at that particular location. And so we can plug in a point into the equations and get individually the dr dt and df dt, and that collective piece of information tells us a great deal of what's going on the plane, on the RF plane. So whether you're talking about rabbits and foxes or a simple harmonic oscillator, the phase plane isn't reality, but it's a representation of information about reality. So we're going to kind of pull some things together and take a look at some examples in the next video.